Hello everyone, this is Manisha Mishra, Assistant Professor in Mathematics, Applied Science Department at Central News Institute of Technology and Management, Gurgaon. This college is affiliated to Mahasi University, Rohtak. Today I will discuss topic heat diffusion equation and wave equation. In our previous session, I have already discussed about separation of variables related to heat diffusion equation, right? So today I will give a solution of heat diffusion equation applying boundary conditions and also initial conditions, right? And the wave equation I will solve by the method of separation of variables, and I provide a wave equation solution in detail in our next video session. So today I will discuss the whole solution of heat diffusion equation. Right now, this exercise is related to your method of separation of variables. So you guys can solve all these questions related to method of separation of variables, and also answers are here. So solve these questions, and if you guys have any doubt in these questions, you can ask me. Right now, next method is one dimensional heat equation, right? So there will be a 15 marks question. If suppose this question is asking in your exam, so that question will be your 15 marks question, right? So they can ask solve this heat diffusion equation by with boundary and initial conditions, right? Or they can solve, suppose this is a rod of length L, and this is the heat equation, so just solve the equation or proof or something like that, right? So if you have this equation, del u by del t is equal to c square del 2u upon del x2. So there is only one way to solve this equation. Condition whatever is given, uh, don't worry about our conditions. But if you have the equation del u by del t is equal to c square del 2u upon del x2 type, then this equation is called heat diffusion equation or one dimensional heat equation, right? So what is u, x and t? So t is your time, x is your distance, right? That means if you have a rod and at time t you just give a heat to that rod and it will melt. So what is the distance at it will cover? That means what distance it will melting, right? So t is your time, x distance, and u xt is the temperature of the bar at any time t at a point x distance from the origin. So this point is your o, that means origin. This is your x distance, and this is your rod also, and this is your x axis, right? Now, boundary and initial conditions. I told you about all the three equations, means heat equation, wave equation, and Laplace equation with boundary and initial conditions. So basic boundary conditions of the heat equations are u at x0 and time t, then solution also be 0. If your length of the rod is L, then also solution 0. And if your time is 0, then solution will be your fx, right? So temperature function uxt, it means solution of the heat equation. So we need to calculate. What we are doing here, we are just solving the here the temperature function, right? Uxt. So all we have done here, all we will do here only for the temperature function, right? So target to find out the temperature function. So our temperature solution is uxt is equal to summation n is equal to 1 to infinity bn sin n pi x upon l into e to the power minus c square n square pi square upon l square into t. So our target is to calculate this solution. This is your final answer. So where bn is determined from the equation. So to get this solution, so let's start it. Proof. Let the equation for the conduction of heat equation, we del u by del t is equal to c square del 2u upon del x2, right? So this is your heat equation. Now we know that method of separation of variables, all three equations will be solved by the method of separation of variables. Either it is wave equation, or it is heat equation, or Laplace equation. So first, we know that our separation of variable method. So u is equal to xt. We are assuming that the solution of this heat equation is u is equal to xt, where x is a function of a small x and t is the function of a small t. Right now, we need to calculate, we need our del u by del t and del tu by del x2. So what will we do? We just calculate del u by del t. So differentiate u partially with respect to t. Then you will get del u by del t is equal to uh, okay, del u upon x into del t upon del t, and c square will be here. Now del u by del x, that means differentiating u with respect to small x. So c square del x upon x into capital T. Now del 2u upon del x to c square. Second derivative, we need calculate second derivative. So just calculate your second derivative here. Del 2u upon del x2 is equal to c square del 2x upon del x2 into t here, right? Now, substituting these values in equation 1. So, this is your equation 1. Del u upon del t is equal to c square del 2u upon del x2. Just write all these values here. Now, then you can see that separate all these variables. That means t variable will be one side and x variable will be another side. So, after separating these variables, we will equal all these two equations as a constant k. Right now, first taking first and third term, so 1 upon c square t dt upon dt is equal to k, and 1 by x d2x upon dx2 is equal to k. This is our separation method. So just apply here. Now 1 by c square dt upon t, capital T, is equal to k into dt. So just integrating on both sides, then you can see that dt upon t, that means integration log t, kc square t plus log a. So log t minus log a is equal to kc square into t. So log t by a is equal to kc squared into t. Log a is your integrating constant, right? Now, so t is equal to a into e to the power kc square t. If log will be removed from here, then it will be exponential function. So it will convert into an exponential form. So t is equal to a into e to the power minus p square c square into t, right? So this is your calculation for the time. Now for the distance x, so now 1 by x d2x upon dx2 is equal to k. This is your another variable. To solve this differential equation, so d2x upon dx2 is equal to kx. Now we will apply here three cases. I told you that I will discuss our cases in our next previous session. So I am here discussing to your all three cases. So just see carefully. When k is equal to minus p square. Minus p square means when k is a negative integer, right? Negative integer, that means k is equal to minus p square. So d2x upon dx2, just write here your minus p square. So minus p square x d2x upon dx2 plus p square x is equal to 0. We know that this is the differential equation, and it is a second order differential equation. To solve this equation, we will calculate our auxiliary equation. So its auxiliary equation is, put d is equal to m. So m square plus p square is equal to 0. M square is equal to minus p square, and after factorization, minus one value always iota square. So m square is equal to p square iota square. So m is equal to plus minus iota p, right? So we can see here that our roots are imaginary. So for the imaginary roots, we have a solution of the type x is equal to c1 cos px plus c2 sin px, right? Now we have our both of the solution x and t. So just write uxt is equal to, we have assumed xt. So uxt is equal to c1 cos px plus c2 sin px into a e to the power this function, right? Now time for second case. So our second is when k is equal to p square. That means k is a positive integer here. So after putting this value in your this auxiliary equation, d2x upon dx2 is equal to kx. Put this, put here k is equal to p square. So you can see that d2x upon dx2 is equal to p square x. So d2x upon dx2 minus p square x. This is also a differential equation, and this is a second order differential equation. So m square minus p square is equal to 0. M square is equal to p square, and m is equal to plus minus p. So here roots are real and different or distinct. So what is the solution of this equation? X is equal to c1 e to the power px plus c2 e to the power p minus px. So this is our solution, and t solution will be just right here, k is equal to p square. So uxt is equal to final solution. Now case third is when k is equal to 0, right? So d2x upon dx2 is equal to 0. Whole equation will be 0. Now just need to two times integration here. So just one time integration, dx upon dx is equal to c1 is an integrating constant. Again integrating with respect to x, so x is equal to c1x plus c2. c2 again is an integrating constant, right? So we are getting a straight line solution here, right? Now all the three cases have we have already done here, and we have three solutions for each case. Now which solution will be considered? So this is your straight line solution. Second case is your sine and cos function solution, and first case is your exponential solution. So which solution is periodic, right? So we will always consider a periodic solution. So a straight line is not a periodic function. Exponential function is not a periodic function. Only sine and cos functions are the periodic functions, right? So case second and case third are not periodic function. E to the power px and e to the power minus px and a straight line solution are not periodic. But case first means sin x and cos x are the periodic functions. So we will always consider the sin x cos x solution will here. That means we will consider case 1 here, right? So your final solution uxt is equal to c1 cos px plus c2 sin px into this one, right? It means this is your case 1 case 1, right? You can see that this is your case 1, this solution uxt is equal to this one. So we will consider this solution. Now if we have our solution, then next step our will be apply boundary and initial conditions. So our boundary conditions are when at x is equal to 0, your solution will also be 0. So put x is equal to 0 here. So 0 is equal to c1 cos 0, c2 sin 0 into this solution as it is. 0 is equal to c1 into this solution. Now here, if this solution a into e to the power minus p square c square into t will be 0, that means our time is 0, right? That means our time is being 0 here. That means this solution can never be 0. So our constant c1 will be 0 here, right? Put the value of c1 in star equation. So you will get uxt is equal to c2 sin px into this solution. Again apply second boundary conditions. So at x is equal to L, your solution, your temperature also be 0. So 0 is equal to C2 sin PL into A into e to the power minus p square c square t. Now again we can see here that this solution can never be 0. C2 into a into this constant, these are two constant, and exponential function can never be 0, because if it's constant and this solution will be 0, that means our double star equation also be 0, and it is not possible because we have a solution here, right? So sine PL must be 0. So sine PL is equal to 0. So in sine 0 form, so sine PL is equal to sine n pi. So we are getting here, P from here, right? So our P is equal to n pi upon L, where n is any integer. So put the value of P in double star equation. So uxt is equal to C2 sine Px means n pi x upon L into a into e to the power minus n square pi square upon L square into c square into t, right? So we can see that we are getting a solution here, right? Now after getting the solution, what will be the our next step? uh, 1 minute, right? So you can see that u is equal to this one. So c2 into a, you can choose another constant as a bn. So u is equal to bn sin n pi x upon L into this one. So n is a positive integer. That means n can be 0, 1, 2, 3, and so on. So you can write this equation as summation form u is equal to summation 1 to infinity bn a to the power minus n square pi square c square upon L square into t and this function, right? So this is your initial conditions solution. Now, sorry, boundary condition solution. Now, next one, what is your initial condition? So initial condition is your u at x0 is equal to fx. That means your time t is equal to 0 here. So your ux function, your temperature will be fx. So fx is equal to, if you will put t is equal to 0 here, then you can say that you will get summation n is equal to 1 to infinity bn sin n pi x upon L. So that is your final solution. So this question can be asked your 15 marks. So just prepare your question. Now next topic is your related to wave equation. So first, what is wave equation? So wave always moves wave equation, that means consider an elastic string tightly stretched between 2 points O and A. So this is your string, right? When you pull your string, then you after pulling, then you can see that it will moves like a wave, right? So it is its displacement is y here. So let O be the origin and OA as a x-axis. Let y be the displacement at point P x y at any time t. So your wave equation is del 2y upon del t2 is equal to c square del 2y upon del x2. So this is your wave equation. Right now, obtain the solution of the wave equation this. So our target is to solve this wave equation. So for the solution of this wave equation, our method is separation of variables. So consider y is equal to xt, where x is a function of small x and t is a function of small t. Just find del y del t and del y upon del x. Next, del 2y upon del t2 and del 2y upon del x2. Just write both of these value in equation 1. So you can see that x d2t upon dt square c square t d2x upon dx2. So just separate all these terms. One side t terms, another side x term is equal to k. In separation of variables, we always put is equal to k. So just take first and third term here. So 1 upon c square t d2t upon dt square is equal to k, and this equation, right? Now your final equation is d2t upon dt square minus kc square t is equal to 0, and d2x upon dx2 minus kx is equal to 0. So these are the two equations you have. Now For the solution of these two equations, our three cases here, when k is a positive integer, when k is a negative integer, when k is equal to 0. So just apply all the three cases here. So first one, case 1, when k is greater than 0, that means when k is a positive integer. So we are considering p square here, right? So d2t upon dt square minus p square c square t is equal to 0. So we are taking k is equal to p square. Its auxiliary equation will be m square minus p square c square is equal to 0. M square is equal to p square c square, and we are getting the roots are real and different. So our case is t is equal to c1 e to the power pct plus c2 e to the power minus pct. This is your solution for the time. Now d2x upon dx2 minus kx is equal to 0. So again put k is equal to p square here. So m square minus p square 0. M square is equal to p square. M is equal to plus minus iota p. So our solution is c1. We can take here constant different here c1 c2. You can write here c1 c3 c4. So c1 e to the power px plus c3 e to the power minus px. Now, case second is when k is less than 0. That means our k is a negative integer. So my k is equal to minus p square. So its auxiliary equation will be m square plus p square c square is equal to 0. M square is equal to minus p square c square. M square is equal to I square p square c square. So we can see that the roots are imaginary. So our solution will be c1 cos pct plus c2 sin pct. And for the distance, we can see here that our solution is C3 cos px plus C4 sin px. Now, case third is when k is equal to 0. So d2t upon dtt square is equal to 0 and d2x upon dx2. So again, we are getting a straight line solution, right? These are the three cases depending upon the particular problems, right? Now, we will consider the solution in which function will be periodic. So, in all the three equations, Laplace equation, wave equation, and heat equation, we will always choose a periodic function solution. It means which solution will be periodic, that solution will be considered, and other will be leave, right? So sine and cos functions are the periodic functions, so always we will choose our that solution. So your final solution is y is equal to xt. So c1 cos pct plus c2 sin pct into c1 cos px plus c4 cos sin px. That means we are choosing our case second here. Now in our next video I will share the solution of the wave equation. That means the Lambert solution of the wave equation with boundary and initial condition, because the Lambert solution will be a 15 marks question, and it 99% can be asked in a final semester exam. So prepare that topic, and heat diffusion equation solution is also important. So prepare also this topic, right? So thank you.